Hi, everybody, and welcome to today's edition of the Spectral Geometry in the Cloud seminar. Today, we have the pleasure of having Jade Brisson from the Université de Neuchâtel. Will talk to us about tubes and Steklov eigenvalues in negatively curved manifolds. As usual, if you have any questions during the talk, either unmute yourself or ask them in the chat and we'll relay them. Jade, the floor is yours.
Thank you. So first of all, I want to thank the organizers for inviting me today. What I will be talking about is a joint work with Ara Basmajian, Asma, and Antoine about the Steklov eigenvalues of negatively curved manifolds. First of all, I want to do a little overview of what is known about the Laplace problem in the setting of negatively curved manifolds. So let's take kappa, a positive number between 0 and 1, and n will be a closed connected manifold with sectional curvature in the interval -1 minus kappa squared. The Laplace problem defined on n is defined as the following. So we want to find a real number lambda and a non-zero function u, such that minus the Laplacian of u is equal to lambda times u on our manifold n. And we know that the eigenvalues form an increasing sequence of positive real number, where each eigenvalue is repeated according to its multiplicity. So there's a few results that are known for the Laplace eigenvalues on this specific setting. First of all, in 1983, Schoen proved a lower bound for the first non-zero Laplace eigenvalue for a closed manifold of dimension greater than 3. Namely, it proved that the first non-zero Laplace eigenvalue is bounded below by a constant depending on the dimension and on kappa over the volume square. A few years later, Duduc and Randall proposed a different proof for this result, where they also included the case of dimension 2. And here is a few related works around the Laplace problem. And to finish the overview over the Laplace problem, I want to discuss lower and upper bounds that were given by Schoen, Wolpert, and Yao in the case where we have a surface with negative sectional curvature. So for an integer k greater than 1, they define the following geometric quantity. So they define Lk of n as the minimum of the length gamma, where gamma is a disjoint union of simple closed geodesics that divide n into k+1 components. So for example, if n is the surface drawn in pink and k is equal to 2, the gamma that we're looking at can take the form of the union of the two curves in black. And what they prove is that for every Laplace eigenvalue of index between 1 and 2 times the genus minus 3, we have a bound and an upper bound in terms of this quantity Lk. So in particular, the lower and upper bound shows that if Lk tends to 0, lambda k tends also to 0. And moreover, they provided a lower and an upper bound for the 2g minus 2 Laplace eigenvalue. But in this case, we don't have the quantity lambda k that appears. We only have constant depending only on the genus. And over the years, there have also been further developments around those upper and lower bounds. But what we're interested in today is the Steklov problem. So we need a manifold with a boundary, but whose sectional curvature is also negative. So what we consider is a manifold with totally geodesic boundary and with sectional curvature, again, in the interval -1 minus kappa squared. So here, totally geodesic means that every geodesic on the boundary with its induced metric is also a geodesic in the manifold M. We define the Steklov problem on M as follows. So we want to find a real number sigma and a non-zero function f such that the Laplacian of f is 0 in our manifold. And on the boundary, we want the normal derivative of f to be equal to sigma times f. And we know also that in this case, the eigenvalues form an increasing sequence of positive real numbers, where again, each eigenvalue is repeated according to its multiplicity. So in this particular setting, contrary to the Laplace problem, the Steklov problem has not been studied a lot. So what is known so far is a counterpart of Schoen-Wolpert-Yau's lower and upper bound in the case of dimension 2 and where kappa is equal to 0. So this was proven by Perrin in 2022. What we also know is following lower bound and upper bound proved by Colbois, Giroir, and Hassannezhad. So they provided an upper and lower bound for the K Steklov eigenvalue in terms of the K Laplace eigenvalue of its boundary and also in terms of its rolling radius. And that's pretty much what was known about the Steklov eigenvalues in this specific setting. So what we wanted to do was to find other lower bounds or upper bounds. And in particular, we wanted to find a counterpart of Schoen's lower bound, but for the first non-zero Steklov eigenvalue. A first method to obtain a lower bound is to use the inequality provided by Colbois, Giroir, and Hassannezhad. Why this is a method? Because in this case, the boundary is totally geodesic, which means that its sectional curvature is also in the interval -1 minus kappa squared. So we have access to Schoen's lower bound for the first Laplace eigenvalue. And if the boundary is of dimension 2, we also have access to Schoen-Wolpert-Yau's upper and lower bound. So let's take a look at how the argument goes to find an lower bound, sorry. So we will be denoting B as the number of boundary components. So by the previous inequality, we obtained that the B Steklov eigenvalue is bounded below in terms of the B Laplace eigenvalue of the boundary and the rolling radius. Here, the boundary is a disjoint union of manifolds. So the Laplace spectrum of the boundary is the disjoint union of the Laplace spectra on each boundary component, which means that the 0 eigenvalue is of multiplicity B, and thus the B Laplace eigenvalue of the boundary is given by the minimum of the lambda 1s of each boundary component. And when we see this quotient as a function of the minimum of the lambda 1s, we can prove that it's an increasing function in this variable. So if we find a lower bound for the minimum of the lambda 1s, we find a lower bound for sigma b. And we have such a lower bound, it is given by Schoen's lower bound. So each lambda 1 is bounded below in terms of a certain constant and over its volume square. So the minimum is bounded below by the constant over the maximum volume of the boundary component square, which I will be denoting by A. And when we replace this in the inequality above, we obtain a lower bound for sigma b in terms of the maximum volume of the boundary component, but also still in terms of the rolling radius. So now we can ask ourselves, can we find a lower bound only in terms of the quantity A? Which means, can we find a lower bound for the rolling radius in terms of A? Well, this is achieved by the tubular neighborhood theorem. So a first kind of tubular neighborhood theorem dates back to Schoen, who proved that any closed geodesic in a hyperbolic closed manifold admits a tubular neighborhood of a size depending only on its length. And moreover, the size of the tubular neighborhood increases as the length of the geodesic decreases. A few years later, Basmajian extended this result for a hyperbolic manifold of dimension greater than 3. So what he did, he proved that any totally geodesic hypersurface in a closed hyperbolic manifold admits a tubular neighborhood of a size depending only on the volume of the hypersurface. And just like the case, the two-dimensional case, the size increases as the volume decreases. But this is only for the hyperbolic case, so when our kappa is equal to 1. But we want to have a similar result when the sectional curvature varies in our interval -1 minus kappa squared. And this is what we did. So namely, we prove exactly the same thing, meaning that any totally geodesic hypersurface in a closed negatively curved manifold admits a tubular neighborhood whose size depends on its volume. And in the remaining of the talk, the size of this tubular neighborhood will be denoted by W n kappa of A. And again, the size of the tubular neighborhood increases as the volume decreases. And moreover, we proved that the tubular neighborhoods of disjoint closed totally geodesic hypersurfaces are mutually disjoint. So why am I talking about this? Let me recall that what I wanted to do was to find a lower bound for the rolling radius in terms of the maximum volume of the boundary component. So the rolling radius is the radius of the maximal ball that can be rolled around the boundary and still be contained in our manifold M. So the rolling radius must be greater than the size of each tubular neighborhood and our boundary component. And since the size of the boundary, the size of the tubular neighborhood increases as the volume decreases, the size of each tubular neighborhood is always greater than the size of the tubular neighborhood of the boundary component that admits the maximal volume that was denoted by A. And moreover, we were able to obtain a lower bound where the dependency on A was explicit, so a lower bound for the size of the tubular neighborhood, so for W n kappa of A, where the dependency on A was explicit. So with this lower bound, we can replace it in the lower bound that we had before for sigma B in order to prove the following theorem. So all those steps help us to prove that for every manifold with totally geodesic boundary and with sectional curvature in our interval and with dimension greater than 4, the B Steklov eigenvalue is bounded below by a constant depending on n and on kappa over A, which is the maximal volume of the boundary component, to this specific power. So now what is natural to ask is if A is really necessary in this lower bound. And in fact, it is necessary. We can show it by constructing a family of hyperbolic manifolds. So when kappa is equal to 1, such that the boundary has two components, its volume tends to infinity, and each Steklov eigenvalue tends to 0. And moreover, we will prove at the end of the talk that we cannot find such a bound for eigenvalues of lower index. So for eigenvalues of index between 1 and B minus 1, only if B is greater than 1. So this is a result in dimension 4, we can ask, can we have a result in dimension 3? Well, yes, we can use the same steps, but instead of using Schoen's lower bound for the first non-zero Laplace eigenvalue, we use Schoen-Wolpert-Yau's lower and upper bound. So we obtain the following result. So for a 3-dimensional manifold with totally geodesic boundary, and also again with sectional curvature in our interval -1 minus kappa square, we will denote G as the genus of the boundary. So it is equal to the maximum of each genus on the boundary component. A is again the maximum volume of the boundary components, and L1 of del M is equal to the minimum of the quantity L1 that I defined before when I was talking about Schoen-Wolpert-Yau's bound. So with this notation, we prove that the B Steklov eigenvalue is bounded below by a constant, now depending on the genus, and on kappa times the quantity L1. And when we have one boundary component, we can say more. So we obtain a lower bound and an upper bound for the Steklov eigenvalues of index between 1 and 2g minus 3. Those bounds depend on the quantity Lk, but when we're looking at the 2g minus 2 Steklov eigenvalue, the lower and upper bound don't depend on the quantity Lk anymore. So we can see that when we have one boundary component, we obtain in both cases, so when we have dimension 3 and dimension greater than 4, we obtain a lower bound for the first Steklov eigenvalue, which is something that we wanted to do. But when B is greater than 1, we don't have yet a lower bound for the first non-zero Steklov eigenvalue. So we need to find another method if we want to find such a lower bound. And this is what we did. So in fact, we observed that we could adapt Dodzik and Randall's proof for Schoen lower bound, but to the Steklov case. And by doing so, we obtained the following theorem. So for a manifold of dimension greater than 3 with totally geodesic boundary, if A denotes again the maximum volume of the boundary components and V is the volume of our manifold, we have that sigma 1 is bounded below by a constant depending again on the dimension and on kappa over the number of boundary components times V squared times A to this power. So here again, we can ask which quantity is necessary. In this case, we can show that V is necessary by constructing a family of manifolds with B boundary components. B must be strictly greater than 1. And this family satisfies the following. So the volume tends to infinity, the volume of the boundary is fixed, and the B minus 1 Steklov eigenvalue tends to 0. And moreover, we can prove that the rate of convergence is 1 over the volume of our manifold. And in a few minutes, I will show you this construction. But before, I want to do a little recap of the lower bounds that we have so far for the first non-zero Steklov eigenvalue. And more precisely, in the case where we have one boundary component, because in this case, we have the lower bound given by this following theorem, but we also have the lower bound that were given by the previous results. So in dimension 4, sigma 1 is greater than the maximum between the two lower bounds. And naturally, we can ask which lower bound is better in which case. And we observe that when A is large, the first term, so our first lower bound, gives a better lower bound. in dimension 3, again, sigma 1 is greater than the maximum between our two lower bounds. So as we can see, we have the first lower bound in terms of L1, but the second term in the maximum is slightly different than the previous lower bound in the theorem, because we don't have the A anymore. We only have a constant, and we have V squared on the denominator. This is because we can modify the lower bound in this case. Why? Because in dimension 3, it means that the boundary is a surface of dimension 2. And since the sectional curvature has a lower bound and an upper bound, we can find lower and upper bound for its volume by the Gauss-Bonnet theorem. So the lower bound becomes a bound with a constant depending only on the genus and on kappa over V squared. And again, we ask which lower bound is better than the other and in which case. But here, we don't know, for example, if V must tend to infinity as L1 tends to 0. So we don't know which lower bound is better than the other. So now what I want to do is to prove the necessity of V in our previous lower bound, so in the theorem here. So what we will do is we will construct a family MJ such that sigma B minus 1 tends to 0 and the volume of MJ tends to infinity. So in order to construct our family, we start by taking a manifold with B boundary component, B again strictly greater than 1. The boundary again is totally geodesic, and the sectional curvature of M is again in our interval -1 minus kappa squared. So here V will be equal to the volume of M. Sigma J will be the boundary components. The volume of sigma J will be denoted by AJ, and A is the maximum of all the AJ. So before constructing the MJs, we will construct auxiliary manifolds. So first, for I between 1 and B, we construct the manifold M1I by taking 2 copies of M and gluing them together along the corresponding boundary components, except for sigma I. So we glue sigma 1 with sigma 1, sigma 2 with sigma 2, etc., except for sigma I. So M1 is a manifold with 2 boundary components, each isometric to sigma I. And moreover, I will keep track of the volume of each manifold in our construction. So here, the volume of M1I is equal to 2V, because we have 2 copies of M. Then, for J greater than 2, and for each I between 1 and B, we construct the manifold MJI. To construct MJI, we take M1I and MJ minus 1I, and we glue them together along one boundary component. So again, MJI has 2 boundary components, each isometric to sigma I. And moreover, the volume of MJI is equal to 2J times V, because we have J copies of M1I in MJI, and the volume of M1I was equal to 2V. And now, with those auxiliary manifolds, we can construct our real family MJ. So we fix J greater than 1, and we construct MJ by taking back our puzzle piece M that we consider at the beginning, and on each boundary component of M, we glue MJI. So along sigma 1, we glue mj1, along sigma 2, mj2, etc. So we can see that mj has b boundary components, each isometric to 1 sigma I. So the volume of the boundary is fixed, but the volume of mj, so the volume of mj is equal to the volume of m plus the volume of each mji, which was always 2jv. So the volume of mj is equal to v plus b times 2jv. So we can see that the volume tends to infinity as j tends to infinity. So this is our family. Now, again, what we want to do is to prove that the b minus 1 Steklov eigenvalue tends to 0. We will do this by taking the variational characterization of the b minus 1 eigenvalue. And in order to do so, we need to construct a test function. So we fix j greater than 1, and we will construct the test function on mj. So for I between 1 and b, we construct fji as the following. So fji has a compact support on mji. So it is 0 everywhere except on mji. And on mji, we have this definition. So 1 minus the distance between x and sigma I over the distance between sigma I and mj minus mji. So we can see that the FJIs are mutually disjoint. And for x in our component mji, the square norm of the gradient is bounded above by 1 over the distance square between the boundary component sigma I and mj minus mji. And this distance can be bounded by the following. Okay, so the distance between sigma I and mj, except mji, is the distance between the boundary component sigma I and the sigma I that is attached to m. So it's equal to the distance between the two sigma I that we can see in the drawing on this slide. We constructed mji by gluing a certain number of copies of m. So we have a certain number of sigma i's in our component mji. And if you remember, we had a tubular neighborhood theorem that states that we have a tubular neighborhood of a size depending on the volume around our boundary component. So around sigma I, there exists a tubular neighborhood of a size depending only on its volume. So visually, we can see that the distance must be greater than when we add the sum of each tubular neighborhood. So how many tubular neighborhoods do we have? We have 2j such neighborhood, and the size is always W n kappa of AI, where AI is the volume of sigma I. But again, as I said when I stated the tubular neighborhood theorem, the size of the tubular neighborhood increases as the volume decreases. So each W n kappa AI is always greater than the size of the tubular neighborhood, the boundary component that admits the maximum volume that I denoted by A. So with this lower bound for the distance, we obtain an upper bound for the square norm of the gradient. And now we can use this in the variational characterization. So sigma b minus 1 is bounded above by the maximum of the Rayleigh quotients of each FGI. So FJI has compact support in the component MJI. So the numerator of our quotient is bounded above by the bound that we had before for the square norm of the gradient. Since it's a constant, we only have the constant times the volume of MJI. And for the numerator, well, again, FJI is only supported on MJI. So the integral on the component is only equal to the integral on the boundary component sigma I. And since FJI is equal to 1 in that case, we obtain the volume of AI, of sigma I, which is AI. So now we use the fact that the volume of MJI is equal to 2JV. So the only thing that depends on I here is AI. And the maximum of 1 over AI is equal to 1 over the minimum of the AIs. So here we simplify a little bit and we express J. So let me just come back to. So here we have an expression for the volume of MJ in terms of J. So we can find an upper bound in terms of J times something. And we can use this bound to change the J here on the denominator to appear the volume of MJ. Because yes, we wanted to show that sigma B minus 1 tends to 0 as J tends to 0. So we can obtain it with the first quotient in the second line. But we also wanted to prove that the rate of convergence was 1 over the volume of MJ. And since we don't have it, we need to make it appear. So that's why we bound below 1 over J in terms of the volume. So we obtain the following quantity in the second line. So we have proven that the volume of our manifold is necessary in our lower bound for sigma 1. And moreover, when I presented the first result, so the result for the lower bound for sigma B, which was only in terms of the maximum volume of the boundary component, I said that such a bound fails for the eigenvalues of lower index. So for example, we cannot have a lower bound for sigma B minus 1, which is the form a constant over the maximum volume of the boundary component to a certain power. And why such a bound fail? This is because of the result that I just shown. So if we had such a bound, sigma B minus 1, for sigma B minus 1, well, this bound would also apply for our family here, MJ. Sigma B minus 1 tends to 0. So if we have a lower bound in terms of A, this lower bound must also tend to 0, which means that the volume of the boundary must tend to infinity. But here, the volume of the boundary is fixed since it is equal to the volume of the boundary of our puzzle piece that we consider at the beginning, M, which was fixed. So we cannot find a lower bound for the eigenvalues of index between 1 and B minus 1, only if B is greater than 1. And this is what I wanted to talk about today. Thank you very much.
Merci, Jade. Thank you very much. We have time for questions now. So if you have questions, please unmute yourself or ask them in the chat and we will relay them here.
I'll start to have a question. So can this condition on the boundary being totally geodesic be relaxed in any way?
Well, I think it can be relaxed, but I don't think we would obtain the same results. Because it's really important when we use the tubular neighborhood theorem, because it's only proven for a totally geodesic hypersurface. So if it's not totally geodesic, we cannot say that the boundary component admits a tubular neighborhood of a size depending only on the volume.
Yeah, so basically you would probably get something similar, but with other geometric quantities entering in.
Yeah, probably, yeah.
Anyone else wants to ask a question to Jade? So I had a similar question regarding another of your assumption. If you had manifolds that have positive curvature but bounded, say instead of 0 to some negative, like what would change? Do you know?
I don't know. Well, first of all, I don't know if there's a tubular neighborhood theorem in that case. And yeah, I don't know if there's like, if we could maybe adapt the proof for the first results, so the bound for sigma b. I don't know if there's like upper or lower bound for the Laplace eigenvalues in that case.
Yeah, true. Yeah. So here the negative curvature is what allows you to go beyond what Bruno, Asma, and I did with more general bounds, but less specific. Yeah. Thank you. Anyone else wants to ask something to Jade? If not, let's thank Jade again. Thank you very much. Merci beaucoup, Jade. And let me announce next week. Next week, we will have a talk by Chang-Wei Xiong, who will speak about the weighted Rayleigh formula for differential forms and sharp Steklov eigenvalue estimates. So thank you very much, everyone, and have a great week and safe week until then. Thank you. Bye-bye.
Thanks a lot for your talk.